Today I wanted to talk a little bit about the network layer characteristics. This is in Module 8. Modules 8 through 13 all deal with the network layer of the OSI model. So the network layer is positioned between the data link layer and the transport layer of the OSI. IPv4 and IPv6 are the primary protocols used for communication. Networking layer performs encapsulation and de-encapsulation and device addressing. In other words, all devices have a unique IP number, and also performs routing as well. Network layer encapsulates the segment, which is the PDU from the transport layer, into a packet. The destination and source IP address do not change along the path, which is different than at layer 2, at the data link layer. The MAC address, the physical address, would change from hop to hop as it went along the network. That doesn't happen at layer 3. IP addressing, it remains the same as the packet traverses the network. IP is a connectionless protocol, best effort and media independent. No connection is established with the destination before sending packets, and there's no way to synchronize, reorder, delivery order, or acknowledge packet delivery in IP. IP is best effort. Packet delivery is not guaranteed. Receiving node does not acknowledge if the packet was received, and the sending node does not care if it got there. IP does not retransmit or fix undelivered or corrupt packets. In order to do that, it relies on other protocols such as TCP when that is needed. And IP does not care about what media the message is sent over. In other words, if it's over wireless or Ethernet or over fiber optic cable, it doesn't matter. It's the same IP packet. It would look the same either way. The data link layer passes the MTU, which is the maximum transmission unit value, up to the network layer. The network layer then determines how large the packet can be based on that information. Fragmentation is something you'll hear about. That happens when IPv4 packets are split into smaller units. That doesn't happen at IPv6. IPv6 does not fragment packets, so that's something to remember. I think there's a test question about that. So let's take a closer look at the IPv4 packet header. It's 4 bytes across 20 bytes deep. It comes with a version. The version is set to 0100, which is binary for 4 for IPv4. DS, or differentiated services, used to be called the TOS field, or the type of service field. It's an 8-bit field used to determine the priority for each packet. Let's see, header checksum, that's used to detect corruption in the header. Time to live, that's an 8-bit number, or 8-bit binary value used to limit the lifetime of a packet. And how that works is the TTL will be set to a certain value, say 12. As the packet goes from router to router, from hop to hop, that number is decreased until it either reaches its destination, or if the time to live ever reaches 0, then the router that receives that will drop the packet. That basically means that that keeps packets from going on forever. If they ever getting in a loop or something, that is a way to stop them from continuing on forever and ever. A protocol that's used to identify the next level protocol. Most common values are ICMP, TCP, and UDP for layer 4. ICMP is layer 3. And of course, the source and destination address, that's the IP address, and that in IPv4 is a 32-bit value. IPv4 has some limitations. We've basically run out of IPv4 addressing. It's only like 4.3 million IP addresses, something like that. It's a finite number. It's not a number that is really all that large when you consider all the devices that can accept an IP number nowadays, especially when you consider like Internet of Things devices, home devices, things like that. We've used something called network address translation as sort of a temporary short-term solution to get by the fact that we're running out of IPv4 addresses. NAT is such a successful solution that it turned into a long-term temporary solution. It's not the best case scenario. It's not was not meant to be a long-term solution. NAT has its own problems. It does some latency and troubleshooting issues. It does slow down the network a little bit. So it wasn't meant to be a permanent solution. And it's not a good long-term solution, even though it is being used in a long-term solution capacity. Switching to IPv6 is a much better long-term solution. Provides pretty much an everlasting number of IP addresses. 340 undecillion IPv6 addresses. That's so close to infinity, you might as well have called it, forever. We're not going to run out of IPv6 addresses anytime soon, if ever. The IPv6 packet header is larger than an IPv4 packet header, but it is simplified. It has fewer actual fields. It's more streamlined, so it's more efficient, even though it's larger. IPv6 eliminates the need for NAT, so that kind of takes out the whole using NAT as a stopgap solution. Take a closer look at the IPv6 header. As I said, it's larger, but it has fewer fields. It has a version, and as you can probably guess, the version is set to 6 or 0110 in binary. Traffic class, it's an 8-bit field equivalent to the differentiated services or DS field from IPv4. Flow label, that suggests that all packets of the same flow label receive the same type of handling by routers. So kind of like a priority field. Payload length, that's a 16-bit field that indicates the length of the data portion or payload of the IPv6 packet. Hop limit, that is actually very much like the TTL fields that's used in IPv4. It's dropped down, it's set to a value and it's dropped down as it goes along its path. Every time it goes through a router, it's decreased by 1, and if it ever reaches 0, it'll be dropped. So it's very much like time to live, hop limit. And of course, it's got the IP address destination and source destination now. In IPv6, this is a 128-bit field per each one, as opposed to a 32-bit field in IPv4. So another aspect of layer 3 is it handles the routing. Let's bring up, I'm going to show you how to do very simple static routing. Here's a packet tracer file. It's got really 3 networks. It's got 2 switched networks and 1 point-to-point network. Now, anytime a network is connected to a router, the router automatically self-learns its routes that are connected. So this router 0, it sees this network, and it sees the other router, this point-to-point. but it does not actually see this network right here, this .12.0/24 network. Now, if I were to ping from PC0, I'm assuming it's set up, to this router, let's delete that one. It should be working. Let's take a look and see why that's not working. Oh, it's dropping right there. So oh, yep, that makes sense. Okay, so let's take a look at that again. So I've just sent a ping from PC0 to router 1. Travels to the switch, goes to the router. Router knows where to send it to. Okay, now ICMP, it uses an echo process where it sends and then it expects to hear back. So in order for this packet to go back, it has to go back to 172.16.11. Or whatever this PC is. This router doesn't know about this network. It's not directly connected. We can see that if we do a show IP route, you can see that 172.16.11.0 is not represented on this. So if we go into configuration mode, nope. No, we're doing a full class C/24. That's 255.255.255.0. Now this is gigabit 00. I could also point it to the IP address for the next hop. But I'm just going to tell it to send this network, which is on here. It's got to go out this interface, which is gigabit 00. Okay. Now let's try that again. We'll just step it through. It's this router now. This router now knows where 172.16.11 is. Oh, it looks like we're running into another problem. So let's take a look at that. Oh, here we go. Okay, that worked. So let's go to simulation mode again. Let's just do it one more time just to make sure it works right. Okay. Now, if we take a look at the routing table again, open this up so you can see it line by line. Before, we didn't have a route for 172.16.11, but now we have statically routed, and that's what that S means, this network right here to go out gigabit Ethernet 00 whenever this router receives a packet for this network. So now let's take a look at pinging from the other network. Now this should, because we have set up this router with this network, this should get there, but it should fail on the way back. Let's take a look. Oh, let's try that again. Step it through. Router 1 sees that it's a packet destined for 172.16.11.0 or dot 10 or whatever this IP number is. It's in this network. Sends it out gigabit 00. This router is directly connected to this network, so it knows about it. So it passed it along out gigabit 01. The switch knows where it'll look for it. And now on the echo back, this router doesn't know about this network. So the packet gets dropped right there. Pay attention to that. That's something separate. Let's go to real time. So let's take a look at router 0. If you look at the routing table on router 0, you'll see that 172.16.12 is not listed on here. So we need to add this network to this routing table. And again, it's the interfaces for this point is both on the router's gigabit 00 port or interface. And let's redo that last ping from PC3 to PC0. And it gets there, it got there before, but now we should be able to receive the echo response. We did this last time. Go to real time. It's a packet tracer thing. There we go. And that's how static routing works in a nutshell. So this packet tracer example is actually in your WebEx Teams. Pull that over here. You go on to WebEx Teams, you go to your ITN 8 modules 8 through 13. You get this page where there's messages, shows you people that are in the group, and under content, you'll see some files that have been uploaded, and this is simple static example, simple static routing example mod 8. Just click on here, you can download it and you can play with this.